Section 1.4, now we are looking at functions, okay? So we want to get our definition of a function down, make sure we know what sets it apart from those equations in the last couple of sections. So a function f from a set A, so a group of values, to a set B, another group of values, is a relation that assigns to each element x in the set A exactly one element y in the set B. The set A is the domain or set of inputs of the function f, and the set B contains the range or set of outputs. So that's a real textbook definition. Okay, let's simplify that down a little bit and be concise and say what we really need to say. And it would help if I could spell things correctly. Just each input has only one output. Every element in the domain, set A, has only one value assigned to it in the range, set B. So if you have an input, there's only one output assigned to match up with it. Now, that output can go to a bunch of different inputs, okay? Maybe every single input has the same output. That's fine, as long as each input only has one corresponding output. Each domain value goes to only one range value. And all of your domain values, they can all go to the same range value, same output. They can all converge on this one piece, okay? So like here they got kind of an idea, time of day, temperature, okay? In case you don't know, sometimes the temperature repeats itself during the day, all right? So at 1 o'clock, it's 9 degrees. So obviously it's winter, or maybe, you know, May. We live in Michigan. 2 goes to 13. 3 and 4, not a whole lot of change at 3 and 4 o'clock. It stayed 15 degrees the whole time, but that's okay because 4 o'clock isn't 15 degrees and 13. Okay, what's the temperature out? It's 25 and 27 degrees. All right, what's that? So each input has only one output. Some characteristics you can read through here. I'm not going to take the time with that right now. Let's look at some examples, okay? Each input has only one output. Now let's look at a table of values, okay? So 0 and input values going to -4. Okay, that's cool. Just going to -4. 1 is going to -2. Cool. Just going to -2. 2 is going to 0. Cool. It's just going to 0. 1, hold on. Now, wasn't 1 going to -2? But now look over here. All of a sudden, 1 is going to +2 also. So this single input value, 1, is going to 2 different numbers at the same time. That kind of breaks the definition. And just to seal the deal, look at 0 and 0. 0 going to -4, 0 going to +4. So no, this is not a function. When you're given a table of values, sometimes it helps look at your x values. If you ever have x values repeating themselves, you probably got a problem, okay? Over here, 0 going to 3. All right. 3 going to 3. Okay. 9 going to 3. 12 going to 3. 15 going to 3. This is like in the Bahamas. It's like within 5 degrees all day. It's humid, but it's predictable. So, 0 to 3, 3 to 3, 9 to 3, 12 to 3, 15 to 3, they're all going to 3. They're all going to 3. Now, they're all going to the same value, but 0's only going to 3. It's not also going to something else. So, yes, it's a function. Again, with a table of values, look, are the x values getting repeated? Is a single x value coming up more than once? Chances are that is not going to be a function. Cool kind of function we look at in calculus a lot, a piecewise defined function. So some type of scenario or relationship, depending on your input, you have a different rule that governs it. Okay? So x squared plus 1. That is the function rule if we're working with negative values. X is less than 0. But once x becomes 0 and becomes positive, we switch to a linear function, x minus 1. So evaluating at these certain values here, f of negative 1, f of 0, and f of positive 1. Depending on your input, you have to look at the function rule you're going to be using. So negative 1, that is less than 0. That is negative. When it's less than 0, we use our quadratic model. X equals 0. That's right at that cutoff, that transition point. All right, that means we're going to be plugging it now into the linear function. And when we're positive, greater than 0, again, plugging it into that linear function. And then you can do some quick calculations, and you have everything you need. So piecewise functions, the only difference is there's multiple function rules. You are going to be using the function rule that corresponds to your restrictions. Where is your x value? That's going to tell you what function rule to use. Now, domain and range. I'm really big into specificity, okay? My favorite word, specificity. Just like say it to yourself. It feels good to say it. Using correct notation, find the domain of each function. So how we are going to write function notation, okay? A big part about learning is being able to read what you're trying to learn. So if you cannot read mathematics, it's much more difficult to learn mathematics. So looking at the symbols, looking at the notation, being able to understand what this foreign language is trying to tell you, translating it back into English. So in this case here, our function f is 5 discrete ordered pairs, okay? So our domain, so D colon squiggly bracket. That's function set notation, all right? So these first ordered pairs, they're x values, and they seem to be from the real number system. So x is an element of the real number system. This vertical line with the exception. So it's not all real numbers. It's just the numbers we have listed here. Okay, that is function notation. The domain is the set, where x is an element of the real number system, with the exception that x only equals those values, -3, -1, 0, 2, 4. Now this exception here can be in the positive or the negative, that it is these values, it is these certain values, or it is not. We're excluding some of these values. So with the exception is open-ended, you got to look over here to see what they're really talking about. So right here, g of x. Now, a rational function. You can plug pretty much anything you want into a rational function. So x is an element of the real number system. Now I said you can plug in almost anything. In algebra, we still have this pesky little problem where we can't divide by 0. So you can plug in anything you want for x, but you cannot get a 0 in the denominator. So we have an exception. X is from the real numbers, but x cannot make that denominator equal 0. So x cannot equal -5. X is a real number with the exception that it cannot equal -5. So let's do like, the bouncing ball that follows along in a song. The domain is the set, where x is an element of the real number system, with the exception that x cannot equal -5. And you close the set. So as you look through these problems here, you want to think to yourself, okay, what type of number could they be? What number system are they from? And then what values work, what values don't? You have to work that exception into there. For example, the volume of a sphere. Okay, you want to find volume of a sphere. Well, you can plug in a whole number, you could plug in a fraction. But do you want that sphere to exist? If you do, then that number you plug in has to be positive. So you have to work that into your exception. All right? So the rest of these examples, also on the previous page, those are in my completed notes online. You can take a look at those.